China's artificial sun, a breakthrough in nuclear fusion technology. For decades, scientists around the world have pursued one of the most ambitious goals in modern physics, harnessing the power of the sun to create a nearly limitless source of clean energy. In this pursuit, China has made remarkable advancements with its experimental advanced superconducting tokamak, commonly known as the artificial sun. This technology represents a massive leap forward in the quest for sustainable energy, offering the potential to revolutionize how the world generates power. In this video, we will explore the artificial sun, what it is, how it works, the science behind nuclear fusion, its challenges, and what this means for the future of energy. What is the artificial sun? The artificial sun is not a literal sun, but rather a nuclear fusion reactor designed to mimic the energy generation process that takes place inside our own star. At its core, the project seeks to achieve nuclear fusion by heating hydrogen isotopes to extreme temperatures, causing them to combine and release massive amounts of energy. Unlike traditional nuclear fission, which splits atoms apart, fusion joins them together, producing a far greater energy output without dangerous radioactive waste. China's most prominent project in this field is the experimental advanced superconducting tokamak, or EAST, located in Hefei Anhui province. To understand why China's artificial sun is so significant, we first need to understand the science of nuclear fusion. Fusion occurs when atomic nuclei merge to form a heavier nucleus, releasing enormous amounts of energy in the process. The most common fuel for nuclear fusion experiments is a mixture of deuterium and tritium-2 isotopes of hydrogen. Under extreme pressure and temperature conditions, these isotopes collide with enough force to overcome their natural repulsion, fusing into helium and unleashing an extraordinary amount of energy. The sun achieves this naturally because of its immense gravity, which creates the necessary conditions for fusion to occur. However, on Earth, scientists must replicate these conditions using advanced technology and magnetic confinement techniques. This is where the tokamak design comes into play. Understanding the tokamak design, a tokamak is a donut-shaped magnetic confinement device that uses powerful magnetic fields to control and contain superheated plasma. Plasma, the fourth state of matter, is created by heating gas to extreme temperatures, causing electrons to separate from nuclei. In the case of EAST, scientists heat plasma to over 100 million degrees Celsius, nearly 7 times hotter than the core of the sun. This intense heat is required to create the right conditions for nuclear fusion. Because no material on Earth can withstand such high temperatures, magnetic fields are used to confine the plasma, keeping it from touching the reactor walls. The magnetic fields generate a stable environment, allowing scientists to sustain the reaction long enough to produce significant amounts of energy. China's breakthrough with East China's artificial sun project, EAST, has set multiple records in nuclear fusion research. In December 2021, it sustained a plasma temperature of 70 million degrees Celsius for over 17 minutes, a groundbreaking achievement in the field. More recently, in 2023, it reached temperatures of 100 million degrees Celsius, lasting for hundreds of seconds, further proving the viability of controlled nuclear fusion. These results represent a crucial step in the journey toward commercializing nuclear fusion power. Sustained plasma temperatures at these levels show that China's artificial sun is edging closer to creating a reliable and continuous fusion reaction, bringing scientists one step closer to achieving net energy gain, where more energy is produced than consumed. Comparing China's artificial sun to other global projects, China is not alone in the pursuit of nuclear fusion. Several international projects are also striving to achieve commercial fusion power. The most notable among them is the International Thermonuclear Experimental Reactor, or ITER, a collaboration between 35 countries, including the United States, European Union, Russia, India, and Japan. ITER is expected to be the world's largest fusion reactor, aiming to prove that large-scale nuclear fusion can be a sustainable energy source. Additionally, private companies such as Helion Energy and Tokamak Energy are working on smaller fusion reactors, aiming to deliver viable commercial reactors within the next few decades. While China's East Reactor is an experimental facility providing critical insights into plasma physics and magnetic confinement, the goal is to use the knowledge gained from this research to develop future commercial fusion power plants. The challenges of nuclear fusion. Despite its promise, nuclear fusion is one of the most complex technological challenges humanity has ever attempted to solve. Several key obstacles still need to be addressed before fusion energy becomes a practical reality. Energy input versus one of the biggest hurdles is achieving a net energy gain, where the amount of energy produced by the reaction exceeds the energy required to sustain it. Most current experiments, including EAST, still consume more energy than they generate, although advancements in confinement time and plasma heating continue to improve efficiency. Plasma stability, controlling plasma and maintaining the right conditions for sustained fusion is extremely difficult. Tiny disruptions in the plasma can cause the reaction to become unstable, resulting in a loss of confinement. Scientists must develop better ways to stabilize plasma for longer durations to achieve a consistent energy output. Material durability fusion reactors operate at extreme temperatures and intense magnetic fields. The reactor walls must withstand prolonged exposure to high-energy particles without degrading over time. Finding the right materials and cooling systems to manage these conditions remains a significant challenge. Tritium supply. Tritium, one of the primary fuels used in fusion reactions, is scarce and expensive to produce. New methods for breeding tritium within reactors must be developed to ensure a sufficient and sustainable fuel supply for future fusion power plants. The future of fusion energy. Despite these challenges, the progress made by China's artificial sun and other global fusion projects demonstrates that we are moving closer to achieving practical fusion energy. If scientists can solve the remaining technical obstacles, nuclear fusion has the potential to revolutionize global energy production. Fusion power is clean, nearly limitless, and produces no greenhouse gas emissions, making it a key technology in the fight against climate change. China has already announced plans to build a next-generation fusion reactor by the 2030s, with a goal of creating a commercially viable power plant soon after. Similarly, ITER and other projects aim to develop fusion reactors capable of feeding electricity into the power grid within the coming decades. Conclusion: the artificial sun represents one of the most exciting advancements in modern science. As China and the world continue to push the boundaries of what is possible with nuclear fusion, we are witnessing the beginning of a technological revolution that could change the way humanity generates and consumes energy. If successful, nuclear fusion will provide a nearly infinite source of clean power, propelling civilization into a future of abundant energy and environmental sustainability. Until then, the scientific community remains committed to unlocking the secrets of fusion energy, bringing us closer to a world powered by the same force that fuels the stars.